shape. Hope you had a great weekend, everybody. It was nice weather today starting out. It was 71 degrees when I left the house this morning. I'm like, wow, that's a nice change. Makes it feel more springy, maybe even summery, but it's nice. But yeah, we had my grandson's birthday party at the park this past weekend. His birthday was the week before on that weekend, but it was Easter and everybody was busy. And so this weekend, his grandparents and great grandparents from Missouri were able to come down. That's his on his father's side. And so he got to have a good birthday at the park with his little 2-year-old friends out there on the slides and play with bubbles and have some cupcakes, all that good fun stuff. All right, we're missing a few folks. I'm not going to wait very long to get started here because we have a lot to cover this week. Last week we tried to cover 2 lessons and we kind of got in the second lesson and kind of ran out of time. So we're going to finish up that lesson. And I was looking at the next lesson and oh my goodness, there's probably 2 or 3 days worth of stuff in one lesson. We're going to get as far as we can. And if we have to postpone part of this lesson to next week, we'll do that too, because there's a lot. There's a lot in this week's lesson. I don't know why I haven't broke that up in the past. It's like, really, did I leave all of that in one lesson? Apparently I did, because that's what I've used the last couple of years. I don't remember being that stacked, but there's a lot in here. So we're going to get onto that and see how much we can get done in this period. But we'll look at what we didn't really finish up last period, last class. But yeah, last week, let's take a look and see where we're at here. Oh, there's some practice grades down at the bottom. Oh yeah, all my settings are different here. Syllabus order. There we go. That's what I'm looking for. So last week, and I kind of pushed the due date back there. Polynomial functions of higher degree. We didn't really finish that lesson, so we're going to get into that lesson. I said you could do the assignment if you wanted to, or you could wait till this week because I really kind of pushed the due date back. So that's really this week. And we're looking at the real zeros of polynomial functions this week. So we're going to finish up 8.02 and see how far we get. We might or might not get through all of 8.03, but get your pencil and paper, get it warmed up, keep a fire extinguisher handy because we're going to be blazing today. There's a lot here. You made it in time. You're in good shape. Okay, so we're going to go back and see what we did not finish last week with polynomial functions. We looked at general features of graphs. We looked at what happens if it's a negative exponent, or if it's x to the third or x to the fourth, if it's an odd or an even exponent. We kind of looked at the binomial theorem and Pascal's triangle. We looked more at Pascal's triangle than we did the binomial theorem. I want to go through the binomial theorem a little bit to start us out today. But just to review that, Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Got you, Alessandra. 1, 4, 6, 4, 1. That's the coefficients. So this would be for like a binomial to the first degree. And this would be 0 degree, first degree, second degree, third degree, fourth degree. So with like a plus b to the fourth degree, this would be the coefficients that you would use when solving that. 1, 4, 6, 4, 1. See, 1, 4, 6, 4, 1. That would be the coefficients out front, and then you do this. So let's look at this, because I want to look at the binomial theorem too. This was a little bit confusing, but they're related. Pascal's triangle is actually simpler than the binomial theorem. But I'm going to put this up on the screen. We're going to kind of play with this. Get the lighting adjusted to where it's not bleaching us out there. Guess that'll be as good as it gets. So I wrote down the binomial theorem's formula here. NCR equals n factorial r factorial divided by r factorial n minus r factorial, where r would be 0, 1, 2 up to n, and n would be the degree of the binomial that we're using. since this is a binomial theorem. So if we have a plus b to the n power, that gives us our n. And r does everything up till we get to n. So I was doing this for example. We were doing x minus 3 to the fourth power. So n would be 4, right? Fourth power, n would be 4. So we would do 4, the coefficient of 0, 4 coefficient 1, 4 coefficient 2, 4 coefficient 3, 4 coefficient 4. Where r would be everything up to counting until we get to 4. 0, 1, 2, 3, 4. So let's work out what the factorial, what the number is, the coefficient there, using this formula. So I'm going to bring the calculator up. So starting with this one, starting with right here, n. What is n? N is 4. N is the number before the c. And r is the 0. So if we do 4, I'll bring this right up here. 4, and there's a factorial button on the calculator. Most calculators have one somewhere. In exclamation mark, it's factorial. So this would be 24 divided by, and then we'll put this in parentheses, r factorial. 0 factorial is actually 1. 1 times 4 minus 0. N minus r, 4 minus 0. So that's 4 factorial times 4 factorial. So really it's 24 divided by 24. This is just going to be a coefficient of 1. All right, let's look at the second one here. R is now 1. So we're still going to have 4 factorial on top, which is 24. I can kind of write this here. 24 divided by r factorial. Well, 1. 1 factorial is just going to be 1. Right? So this is 1 times, and then we have 4 minus 1. 4 minus 1. So 3 factorial. 3 factorial is 6. So 24 divided by 1 times 6. 24 divided by 6 is 4. So that gives us a 4 as the coefficient of the second term. Then we'll do the same thing with the rest of these. And so they're all going to be 24 on top, because that's 4 factorial every time. Right? So that doesn't change. What changes is the number on the bottom. So now r factorial is, r is 2. So we would take 2 factorial, which is just 2. And then n minus r, 4 minus 2. 4 minus 2. Well, that's again just 2 factorial. That doesn't change. 2 times 2. So 24 divided by 4, that's 6. Now let's do 4 and where r is 3. So we have 3 factorial, which is 6, times, and then it's n minus r, 4 minus 3, 1 factorial. Well, 1 factorial is just 1. So 24 divided by 6 is 4. And then the last one is going to be r is equal to 4. So 4 factorial is 24, because that's what we have on top. 24 divided by 24 times 4 minus 4. Well, 0 factorial is just 1. So this is just 1 because it's 24 divided by 24. So we used the binomial theorem to figure out the coefficients that would go in our formulas. 1, 4, 6, 4, 1. Well, that's interesting, because if we go back here, that's the same thing we get with Pascal's triangle, 1, 4, 6, 4, 1. So that's why they're related. The binomial theorem and Pascal's triangle, either one will get the same numbers. There's the 1, 4, 6, 4, 1. And then to actually solve this, let's go back and look at how does that help us? If we're finding x minus 3 to the fourth, we have a equals x, b equals negative 3. If we're doing a plus b squared. And there's a pattern to solve this. A plus b to the fourth, or x minus 3 to the fourth. The first term, the a, would be a to the fourth in the first term. It would be a to the third in the second term, a squared, a the first, and a to the 0. And the b term would be exactly the opposite. So the first term would be b to the 0. This would be b to the first. This would be b squared. This would be b to the third. And this would be b to the fourth. And all those terms would be added together. So anytime you're multiplying binomials of higher degree, this is the pattern you'd have. The a in the first term would be the highest degree, 4, and it would go down 1 each time. Where b is exactly the opposite. It starts at 0 and goes up until it reaches this number. So if we're doing this, x and negative 3, we would have these coefficients, 1 x to the fourth and negative 3 to the 0 power. Negative 3 to the 0 power. So that's nothing, right? It's just 1. Negative 3 to the 0 power is just 1. So we don't have to put anything there. Plus, this would be the coefficient 4 times, this would be x to the third, and b to the first times negative 3. That's b to the first power. We could put a first power on it, but it doesn't change anything. Then the next term, we've done this term, we've done this term. This would have a coefficient of 6, according to the binomial theorem and according to Pascal's triangle. So with that 6, now we have a squared, x squared, and b squared, negative 3 squared. Okay, that's the third term. The fourth term would have a coefficient of 4. Then we have just an a to the first term, just x. And we have b to the third power. That's a 3. Negative 3 to the third power. And then the last term just has a coefficient of 1. X to the 0, which, x to the 0 is just 1, so we don't need that. And b to the fourth, negative 3 to the fourth. Simplify that, and we will have x minus 3 to the fourth. So this is just x to the fourth. Negative 3 to the first is just negative 3. So negative 3 times 4 be negative 12x to the third. Negative 3 squared. Well, that's 9. Negative 3 squared is 9. 9 times 6 is 54. And we have an x squared. Negative 3 to the third power. That'd be negative 27. Negative 3 times negative 3 times negative 3. Negative 27 times 4. Negative 108. And we have just an x. And then we have 1 times 1. X to the 0 is just 1. 1 times 1. So those don't really do anything. Negative 3 to the fourth power is 81. This is x minus 3 to the fourth. It's x to the fourth minus 12x to the third plus 54x squared minus 108x plus 81. If you want to check that, just take, and I'm not going to do this in the sake of time, but if you take x minus 3 to the fourth power, which means you're multiplying all of those together, you can do that manually. Multiply x minus 3 minus x minus 3. Whatever you get, multiply that times x minus 3. And whatever you get, multiply that by x minus 3. But you should end up with this. The binomial theorem gives us a shortcut, kind of, rather than doing that 4 times, to end up with what this would equal. Pascal's triangle would give us the same thing here. This was to find, these coefficients, which Pascal's triangle gives us even easier. Looking at that. And remember, you add the two above it to get the next one. So the next one would be 1, 5, 10, 5. No, 10, 10, 5, 1. It just gets bigger. The ones just keep going out. And you just, to get the middle terms, you add the ones above it together. So we went over Pascal's triangle. We didn't really cover how this binomial theorem works. So that's why I wanted to get that in our notes. And you can test it on these two to see if you can get the right answers. Check your answers right there. You can check on that. The leading coefficient, we talked about that, whether it's a negative or whether it's a big number, it makes it skinnier, different things that happens. Zeros, we talked about zeros where, x equals a is a zero of the function. It's also called a solution. X minus a is a factor, and a comma 0 is the x-intercept. Those are all the same thing. So if we had this 2x to the third, x minus 2 minus x minus 1, the solutions would be x equals 0, x equals 2, and x equals 1, right? It's wherever setting these equal to 0 would be. So I want you to find the zeros. Oh, our lesson does have something that we really didn't talk about in here. I mean, our assignment has. If we have an equation like this, equals x times x minus 1 to the third times 2x plus 4 to the fourth. Okay, this is our equation. It says, what are the zeros and the multiplicity? We didn't talk about multiplicity. Multiplicity has the word multiply in there. That's what it's assumed, right? So it's talking about how many of these zeros. Now, this is x times x to the third times x to the fourth. There's 8 solutions. This is an x to the 8th. If we multiply all these together, our largest term would be x to the 8th. But how do you know the zeros? Remember, if this is in factored form, which this is factored, you set them each equal to 0. To figure out what these zeros are. Of course, this one's already done. This, we just add 1 to both sides. So this is another 0, because x minus 1. And 2x plus 4, subtract 4 from both sides. 2x equals negative 4. X equals negative 2 is a 0. So if it wants to know what's the zeros and their multiplicity, the zeros are 0 is one of them. 1 and 1 has a multiplicity of 3 because there are 3 of these. X minus 1 times x minus 1 times x minus 1. Multiplicity of 3. There are 3 zeros at 1. And negative 2 is another 0. And it has a multiplicity of 4. Multiplicity of 4. So if you want to know what are the zeros of this equation, the zeros are actually 0, 1, 1, 1, negative 2, negative 2, negative 2, negative 2, but we don't write it that way. We write it like this. It's 0, 1, and negative 2. 1 has a multiplicity of 3. Negative 2 has a multiplicity of 4. But this is what that means. Multiplicity of 3 means there's 3 of them. Multiplicity of 4 means there's 4 of them. Another thing in our assignment that it didn't really go over much in this lesson is like, what if the zeros are 2 negative, let's say negative square root of 3 and square root of 3? What equation has these zeros? Give me an equation that has these as the zeros. And that's all the information it gives you. And you're like, I don't know. Well, this is where it talks about those 4 things being the same right here. Let's go back to it right here. These equivalent statements. If x equals a is a 0, then x minus a is a factor. If these are equivalent, that means if this is true, this is true. So we can use that property to say if 2 is a factor, that means, if 2 is a 0, that means x minus 2 is a factor. If negative square root of 3 is a 0, that means x minus a negative means plus. This is a factor. And if the square root of 3 is a factor, is a 0, then x minus the square root of 3 is a factor. So this equation has these zeros. Let's figure out what this equation is. Let's multiply these together first. X times x. So this will be out front. We haven't multiplied by that yet. X times x is x squared. X times negative square root of 3 is negative x square roots of 3. Now let's distribute this. Square root of 3 times x is plus x square roots of 3. And then the square root of 3 times the negative square root of 3 is negative 3. The square root of 3 times square root of 3 cancels out the square root, right? So let's simplify that. X minus 2 x squared. Now look at this. We've got negative x squared to 3 and positive x squared to 3. Cancels out. So we just have the minus 3. So this is simplified down. Getting my paper all messy here. Now let's multiply this. X times x squared is x to the third. X times negative 3 is negative 3x. Negative 2 times x squared is negative 2x squared, and then minus 3. So simplifying this, x to the third minus 2x squared minus 3x minus 3. This is the equation that has these zeros. We just have to multiply it together. Multiply it together. Set it up as the factors. X minus whatever this number is. X minus whatever this number is. X minus, and then multiply those together, and that will get your answer. What function has those zeros? This one right here. Well, let's prove that to ourselves. It's like, well, okay, you can say that, Mr. Brock, but is that true? Well, if we graph that, if we graph x to the third, x to the third, minus 2x squared minus 3x minus 3. Is that right? Did I mess up anything there? Minus. Okay, this shows 1, 0. I have messed something up because it doesn't have the right zeros. X squared minus 2x squared. All right, let's look at our math, because somewhere in there our math got off. X plus 3, x minus square root of 3, x squared. Those do cancel out. Plus square root of 3 times minus square root of 3 is minus 3. X times x is x to the third. X times negative 3, negative 2x squared minus 3. Oh, this is a, no. It's not minus 3 at the end. There's where I messed it up. I have to take the negative 2 times negative 3. This is plus 6. The end is a plus 6. I messed up the math on that. Plus 6. I forgot to multiply it last term. If I change this to plus 6, now what are the roots? So is that the square root of 3? Let's put that in our calculator just to verify that. Look, 1.73. That is the negative square root of 3. That is the positive square root of 3, because there's the square root of 3. Negative square root of 3, positive square root of 3, and 2. Those are the zeros for this equation. So that is correct. So that is in our lesson, our assignment for this lesson, and it's based on this part of the lesson right here. That those are the same, and you can multiply those factors together to get that. We talked about the intermediate value theorem. That means if we have, a point here on the graph and a point here on the graph, somewhere in between there, every point exists, because you can't go from here to here without hitting every x in between. Right? We hit every x in between there. There's the x of -1, negative 0.34, 0, 0.6. Every x exists in between there just because it's a graph of a function. It doesn't have any gaps. The extreme value theorem. It says, okay, if we have a function on a closed interval, a to b, so let's change our interval. So we're going to say that we're only going to look at -1 to, let's say, 2. So this says in a closed interval from a to b, which we said is going to be from -1 to 2. That's our interval. Here's x -1, right? X is -1 right there. This end x is 2. Then f of x has a maximum and a minimum somewhere between -1 and 2. It has to. In this case, here's the maximum and there's the minimum. Somewhere between those points, there has to be a maximum and a minimum. Even on an equation like this, x equals, let's see, y equals x. I want that on the next line. Y equals x. If we just look at that from -1 is less than or equal to x is less than or equal to 2. Even that equation has a maximum and minimum. It's at -1 and it's at 2. That is the maximum and minimum, but it says there has to be a maximum minimum somewhere between there. On this one, it's actually over here at -0.53, and the minimum's over here at 1.86. But this is just saying, if you look at a closed interval, only from here to here, not necessarily to eternity to eternity, then there has to be a maximum and a minimum. That's simply what the extreme value theorem is saying. And it graphs it here. And look, there's a maximum and the minimum is there. If we just look from this point to this point. So you find where you want to start and stop and find if there's any peaks in between there. So the extreme value theorem guarantees that on a closed interval, any continuous function has a maximum and minimum. That's kind of like a duh, right? It's like, well, yeah, if I have 2 points and I draw lines between them, even if it's a curvy line, somewhere is going to be the largest value and somewhere is going to be the smallest value. That's all that is saying. So don't get that real confused. Okay, then here is the actual more detail. We just look at the summary because the summary covers everything. This just goes into more detail. So let's go. Let's see. There's the assignment. Find the zeros. Find the zeros. The multiplicity we just talked about. Find something that has these zeros. That's where we multiply them together, the factors. And this is, you expand it using Pascal or the binomial theorem. So we've looked at all of that now. Let's look at the next lesson. This is what was actually supposed to be covering today, but we had to spend half an hour finishing the last one. Let's look at the relationship. So sometimes when we view the graph of a polynomial, we can see a value of x that's a 0. The relationship between an x-intercept and a factor. All right. In the function 2x to the third plus x squared minus 14x minus 21, a graph shows, well, let's put that on a graph to see what the graph shows. So we'll look at the graph ourselves and make this to the second power. Okay. There is the graph of the function they're talking about. 2x to the third minus x squared minus 14x minus 1. The graph that shows 4x equals 3, a 0 occurs. Oh, that is a 0. That's where the function equals 0, right? It equals 0 there. Crosses the x-axis. That is a 0. The only 0 we can see for this equation. Therefore, x minus 3 is a factor. Ah, correct. It is a factor. So let's do this. Let's see, why are they doing this? So they're saying since x equals 3 is a 0, that means x minus 3 is a factor. So what they're wanting us to do is to factor that out. I want to write this down. X minus 3 equals 2x to the third plus 2x. So we can divide this into that. The lighting is not helping us here. We can divide this into that. So the way you do that is, since there's two terms, we take the first two terms here, and we say, how many times does x go into 2x to the third? Well, it goes in 2x squared times. You just divide x out of that. 2x to the squared times x is 2x to the third. 2x squared times negative 3 is negative 6x squared. This works just like numbers, except we've got x's in here. Now we subtract. This minus this is 0, so that goes away. X squared minus negative 6. Minus negative 6 gives us 7x squared. Bring down the next term. Minus 14x. How many times does x go into 7x squared? Well, it goes in 7x times. If we divide x out of it, 7x times x is 7x squared. 7x times negative 3, negative 21x. Subtract. 7x squared minus 7x squared, that cancels out. Negative 14x minus negative 21x. Minus, so we're adding to that, right? Negative 14 plus 21x, 7x. Now let's bring this down. Minus 2. How many times does x go into 7x? It goes in there 7 times. Oh, this is not 2, it's a 21. It's like, there's a 20, minus 21. 7 times x is 7x. 7 times minus 3 is negative 21. If you subtract 7x minus 21 minus 7x minus 21, you get a remainder of 0, which we should get a remainder of 0. If you remember how the remainder theorem says, the factor theorem says, if you get a remainder of 0, that means that is a factor. And we do see it as a factor. So what's left? When you factor this out, now you have 2x squared plus 7x plus 7. When you remove that. And you could find the zeros of this, which, looking at Desmos, this is the only real 0, which means the other two zeros are imaginary. You would have to use the quadratic formula, and you could find out the other zeros. 1 0 is 3, right? 3 is one of the zeros. The other two are imaginary. They got some kind of imaginary, some coefficient in front of that, but it has two imaginary zeros. But we can find that. So let's go back and see what the lesson's saying about this, since we've done that now. When we factor x minus 3, the result is a polynomial of degree n minus 1. Well, what does that mean? That means we started out with a third degree, and after we divide this out, we now have a second degree. That's 2x to the second power. So the problem becomes how to factor out the 0 function. They say we can do that with long division. Now, sometimes a divisor does not divide evenly, right? If we had 2x to the third minus 3x squared minus 2x plus 6, if we divide that by x plus 1, it has a remainder of 3. So that means x plus 1, 2x squared minus 5x plus 3, which is what you get from the division, plus a 3. We got an extra 3 at the end of that. So this is an example of a division algorithm. It states if f of x and d of x are polynomials, so that d of x is not equal to 0, we're not dividing by 0, right? The degree of d of x is less than or equal to the degree of f of x. There exist unique polynomials q and r so that this factor times this factor plus the remainder will equal the original one. So if we divide this and we have this as our quotient, this times this plus the remainder will give us the original equation, which in this case the remainder is 0. So just multiply those together, you'll get back to the original thing. All right, synthetic division. It does talk about synthetic division, which you did in Algebra 2 as well. There's just a quicker way to divide if you have just an x term that we're dividing by. We can look real quick at one of these. Let me write this down and we'll go through synthetic division quickly. Okay, so if we have x to the fourth plus 2x to the third minus 4x, and we want to divide it by x minus 2, we can do this with synthetic division instead of doing it this way. If you have x minus 2, set that equal to 0, add 2, x equals 2. So we're going to divide by 2. With x minus 2, we're dividing by 2. And we're going to do the coefficients. This will be 1, 2, negative 4, 1, negative 6. We bring the first term down. It's a 1. We multiply 2 times 1. It's 2. We add 2 times 4 is 8. 8 plus negative 4 is 4. 2 times 4 is 8. It's 9. 2 times 9 is 18. We end up with 12. So what this says, just doing the coefficients, multiply, add. Multiply, add all the way across. That means if we divide this by x minus 2, we get x to the third plus 4x squared plus 4x plus 9 with a remainder of 12 over x minus 2's because it didn't go evenly. So 12x minus 2's. So when you divide this by x minus 2, you get this. Now, there's a theorem here that tells us one thing, that if we graph this, since this is the remainder, the point 212 is on the graph of this function. What? Yes. We divide by 2. The remainder is 12. So that means the point 212 is on this graph. This is the remainder theorem. For x equals 2, divided into this, the remainder was 12. So that means there's a point 212 on the graph. We're going to graph that and take a look at that because it's like, that sounds a little bit too fabulous to believe, Mr. Brock. X to the fourth plus 2x to the third minus 4x squared plus x minus 6. Okay. And we said that on the graph of this function right here, we divided by x minus 2, we have a remainder of 12. So we're saying the point 212 is on the graph. And looky there. That is actually a point on the graph. 212 is on the graph. That is a pretty cool theorem right there that we can divide that. I'll zoom back out here. But we can divide a number into this and find the remainder theorem tells us whatever the remainder is the point on the graph of what we divided by. 212. And we could have done the division either way. You can do it long division or you can do synthetic division. But there's also another thing. Let's see if they're doing the factor theorem. Okay, the factor theorem. The factor theorem kind of says if the remainder is zero, this is a factor, which it is. This times that will get us back to the original equation. This is a factor. This did not have a remainder zero, so this is not one of the factors. If we factor this into all of its factors, this is not one of them because the remainder was not zero. I will say there's something else that's related to all of this. Synthetic division is the same thing as doing this, f of 2. What is, f of 2 means we just replace a 2 in there. 2 to the fourth plus 2 times 2 to the third minus 4 2 squared plus 2 minus 6. Right? If we have f of 2, that just means we're substituting 2 in for x because this is f of x. So instead of x, we're putting the 2 in there. So 2 to the fourth. 2 times 2 times 2 times 2 is 16. 2 to the third. 2 times 2 times 2 is 8. Plus, times 2. 2 times 8 is 16. 2 times 2 is 4. 4 times 4 is 16. So that's minus 16. 2 minus 6. So that, well, let's see, it'd be, I can put plus 2 and minus 6. We'll simplify that in the next step. 16 plus 16 is 32 minus 16. So 32 minus 16 minus 4. Minus 16 minus 4 is minus 20. So 32 minus 20. Hey, look at there. That's the exact same number we got when we did synthetic division. So you can do synthetic division, or you can substitute the number in to the equation. Either way, this will tell you the remainder. And if that remainder is 0, then x minus 2 is a factor. But it's not. But it will tell you at 212 is a point on the graph. Just like this tells you 212 is a point on the graph. The factor theorem, the remainder theorem. A lot of different ways to get to an answer on there. 212 is a point in the graph. So it wants to test our skills here. Use our calculator to check your answers. Determine the value of the remainder for the following. 1, -1, -2, and 2. So let's do a couple of these. Let's get a new sheet of paper. Find the remainder for the following. F of 1, -1, -2, and 2. So we could do that multiple ways. The easiest thing to do would be the synthetic division, perhaps. 1, -2, we'll do that, and 6. That's just the coefficients with synthetic division. Bring down the first 1, multiply. 1 times 1 is 1. -2 plus 1 is -1. 6 plus -1 is 5. So the remainder is 5 for 1. We could have also substituted in 1 to the fourth power is 1 minus 2. 1 squared is 1. So 1 minus 2 plus 6. 5. -1. Let's do it the other way for -1, just to show we can do it both ways. So this would be -1 to the fourth power minus 2 times -1 squared plus 6. -1 to the fourth power. -1 times -1 times -1 times -1. It's just 1. Because there's 4 of them, so the negatives cancel each other out. This one has -1 squared. Those negatives cancel each other out. So this is just -2 plus 6. So that's the same thing. The remainder is 5 for both of those, which means the point 1,5 and the point -1,5 are both on the graph. because that's the remainder. So pretty quick. Let's look at negative 2. We'll do synthetic division for the first one. 1, negative 2, and 6. Negative 2 times 1 is negative 2. Negative 2 plus negative 2 is negative 4. Multiply negative 2 times negative 4 is a positive 8. So we have a remainder of 14. So the point negative 2, 14 is on the graph. And then we'll just do the f of 2 instead of synthetic division. 2 to the fourth minus 2 times 2 squared plus 6. Just substituting positive 2 in for our x's. 2 to the fourth. 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 times 2 is 4, minus 2. So 2 times 4, so minus 8 plus 6. 16 minus 8 is 8. 8 plus 6. This is 14. So that means the point 214 is also on the graph. Let's graph that and see if that's right. Those remainders of 5 and 14 should tell us that those are points on the graph. Here, I'm going to put the points first and see if it gets there. So we have 1, 5, and we have negative 1, 5, and we have negative 2, 14, and we have 2, 14. So we're saying that our graph will go through all 4 of those points. And our equation that we're graphing is x to the fourth minus 2x squared plus 6. Well, by golly, it does go through every one of those. There it is. All those points are on the graph, so we must have done it correctly. It says you can use your calculator to check your answers. We checked it by graphing it. So the factor theorem says a polynomial f of x has the factor negative k if and only if f of k equals 0, which means if that any of those factors remain 0, then that would have been a factor. None of these are factors. X minus 1 and x plus 1 are not factors. X plus 2 and x minus 2 are not factors. So then you use synthetic division to determine if x plus 1 is a factor. I'll leave that one. You can do that one just for sake of time, but it does have where you can click this and check your answers. Basically, just checking to see if it has a remainder of 0 when you divide. Okay, let's talk about the rational zero test, also known as the rational root theorem. Rational roots. I'm going to write down this. Okay, this has a way, because if we're looking at this, we're like, okay, what are the factors? What are the zeros? What are the possible zeros of this equation? We could do a lot of math and be doing a lot of synthetic division and trying to guess, is it 1? Is it negative 2? Is it positive 2? We could be guessing a whole lot of numbers. But the rational, they call it the rational zero theorem. I've also seen it called the rational root theorem because a root and a zero are the same thing. The rational root theorem says that if we take our P's and Q's, P would be right here. I'm going to highlight this. What are the factors of negative 4? Well, it could be 1 times 4 or negative 1 times 4, or 2 times negative 2 or negative 2 times 2. So really the only factors are 1, 2, and 4, either positive or negative. You know, one of the numbers has to be positive, one has to be negative, but we can get a negative 4 by multiplying those numbers. And for Q, I'm going to highlight with this. It's a little darker, so I don't want to cover up the number. What are the factors of 2? Well, 1 and 2. Right? Could be 1 times 2 or negative 1 times negative 2. But that's the only numbers you can multiply together to get a 2. So the only possible zeros would be P divided by Q. 1 divided by 1, plus or minus, could be a 1. Could be 2 divided by 1, which would be plus or minus 2. Could be 4 divided by 1. Could be 1 divided by 2, plus or minus 1/2. Could be 2 divided by 2, but that's already been covered. 2 divided by 2 is 1, and 4 divided by 2 is 2. So here's the only possible zeros it could be. It could be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/2. But that is the only possible zeros there could be that are rational. There may be some irrational ones. There may be some imaginary zeros. But if we wanted to check to see what the factors are with the zeros, there's only 8 that it could possibly be. So they talk about that right here. They said the P's are positive 1, 2, and 4. The Q's are 1 and 2. So it could be 1/2, negative 1/2, 1, negative 1, 2, negative 2, and 4, negative 4. Now, it does not guarantee that any of these will be zeros. It may be that all of them are imaginary or something, or not. This is just the rational numbers that could be zeros. Now, another thing that they cover here is Descartes' rule of signs. So we can go back to this here and look at the same equation. And we can say, okay, how many times does the sign change? This is a positive. That's a negative. Okay, there's one sign change. This is a negative, that's a negative. This is a negative, that's. So in only one sign change, consecutive coefficients, because there is a missing coefficient in there. This is actually 2x to the fourth. I don't know that it matters though, because this will be 0x to the thirds minus 2x squared minus 4. It's still just one sign change. Positive to a positive, positive to a negative, one sign change. So that means there's only one positive real root. There's one positive real root. So if we find out that 2 is a root, we don't have to check the other ones, 4 and 1/2. Now, there may be some negative ones, but Descartes says the number of times that the sign changes, which it only changes once from a positive to a negative, then it stays negative. That's how many positive real roots there are. And then the negative real roots, you substitute into here. 2 negative x to the fourth minus 2 negative x squared minus 4 times negative x minus 4. You take the original equation, and everywhere there's an x, substitute a negative x, and then simplify. Negative x to the fourth is still just a positive x, because you got 4 negative x's. Negative x squared is a positive, so this stays negative x squared. Negative 4 times negative x becomes a positive 4x, and this becomes a negative 4. So how many times does the sign change here? 1, changes again, 3 negative roots. But the only thing that Descartes won't tell you is how many imaginary zeros are. An imaginary, just now notes, imaginary roots always, I'm going to underline that, come in pairs. So if any of these are imaginary, it could be that there's one negative two imaginary. I'll put that as an or. If there's three, that means there could be three, or there may just be one and there's two imaginary. But there's definitely one positive. Because there's four roots altogether, right? This is a fourth degree equation. So there are four roots. And of those four, one of them is positive, three or one is negative. It's either three or there's one and two imaginary. Why do I say there's one positive guaranteed? Because if that's imaginary, there would have to be two of them. And there can't be two of them because there's only one that's positive. There's only one positive. So if there's one, it's guaranteed one. If it's two, it could be two, or maybe they're both imaginary. There's four, it could be there. Maybe there's four, or maybe there's two imaginary and two real, or maybe all four imaginary. As long as you remember the imaginary roots have to come in pairs, it helps you figure out. Or, you know. But Descartes, pretty cool. Just check the sign changes. Descartes' rule of signs. Descartes' rule of signs says check how many times the sign changes. And it goes over that here in the lesson. The number of positive real zeros be equal to the number of sign changes between consecutive coefficients. Or it will be less this number by multiples of 2. Now you know why it's multiples of 2, because that means it could be imaginary. The number of negatives will be equal to the number of sign changes between consecutive coefficients when you substitute negative x in. So here's some examples. So look at this. 2x to the 7th minus 4x to the 6th plus 5x to the 3rd minus 2x plus 1. How many times does the sign change in here? We go from a positive to a negative to a positive to a negative, negative to a positive. That is 4 times that the sign changed, which means it could have at most 4 positive real zeros. Or there could just be 2 positive real zeros, or maybe there's none. 0, 2, or 4. Because some of those might be imaginary. Now it said, let's investigate the negative roots. Now this is supposed to be raised to a power. What if I can fix that there? Wait, text. There we go. Superscript that. Yeah, that's what I need to do. And superscript 6. And I'll fix that right there in the document. Okay, so if you substitute negative x in and simplify it, now you've got negative 2x to the 7th minus 4x squared minus 5x to the 3rd plus 2x plus 1. How many times does the sign change? Only one time. It's a negative, it's a negative, it's a negative. Oh, it's a positive. It changed, and it stayed a positive. So there's only one negative real zero. We cannot decrease this by multiples of 2 because that needs a parentheses there too. That'd be -1. There's no way to have a negative amount of zeros. So Descartes' rule is helpful in reducing the rational root list. So the possible rational roots of this one, x to the 3rd plus 2x squared plus 5x plus 1. You would get 1, 2, and 4 as the possible roots of this, right? So I got to divide by 6 different numbers to figure out what the roots are. But Descartes' rule says how many times did the sign change? It never changed. It's always positive. So there are no positive real roots, which means we can cut this list in half. +1, +2, and +4 are not even possible. All we have to check is the negatives. So now substitute that negative x in there. We get 3 sign changes. So that means there's either 3 or 1 negative roots. So all we do is test. We only have to test 3 numbers, and we can tell what the roots are for this equation. And when they tested it, they found x equals -1 is a real root. And then they found -2 was not, so they didn't even have to test -4 because there's only one, and the others are imaginary roots. Okay, find the rational zeros of this. Make a list of all possibles. This goes through the P's over Q's. Use Descartes' rule of signs to narrow down your list, and then figure out which ones work. And you can use a graph to check it. So I've got a check your answers right here. So if you want to do those to see if you know what you're doing, there's the answer key on that. So we won't do one of those in class in the interest of time. Let's look what else we got. So there's still more. Oh, we're almost done. We might finish this. Okay, this is really cool. And I was digging into this morning. We have one more test for real zeros of polynomial functions. Another test for zeros of a function is to look at the sign pattern of the last row of the synthetic division process. So we're going to work through an example here. We're going to take this x to the third. We'll turn this paper over. And go through this. What is this talking about at upper bound? We're just going to walk through this, and then we'll talk about how the upper bound works. So if I have this equation, x to the third minus 7x minus 6. Let's check the p's and q's. P is -6. All the factors could be plus or minus 1. Could be, oh, that's, I don't want the 2 down there. 2. 1 and 6 and 2 times 3, right? So it could be plus or minus 2, plus or minus 3, and plus or minus 6. And Q, the coefficient of this is just 1. So this is all the possible zeros, because dividing those by 1 doesn't change anything. So we have 8 possible numbers that could be a factor of this. All right, 8 possible numbers. That's the first thing they wanted us to figure out. It's a plus or minus 1, 2, 3, and 6. And so what they did is they said, okay, let's check 3 first off. We're going to start with 3. So using our synthetic division, the coefficients are 1. There is not a x squared, so it has a coefficient of 0. That's the tricky thing with synthetic division. It has to be x to the third, x squared, x, and the constant. You have to account for every single one of them. And since there's not an x squared shown, we have to add it in there. So this comes down. 1. 3 times 1 is 3. 3 plus 0 is 3. 3 times 3 is 9. We add those. 2 times 3 is 6. 0. 3 is a factor. But let's see what the upper bound thing tells us. Suppose f of x is being divided by x minus c using synthetic division. If c is greater than 0, which it is, our c is 3, and each number in the last row is positive or 0, c is an upper bound for the real zeros. All upper bounds must be positive. So since every number is positive, positive 1, positive 3, positive 2, and 0, 1 or 0, 3 is the upper bound. So when we're testing all of our factors of 1, 2, 3, 6, -1, -2, -3, -6. This is all positive 0. When we did 3, 6 is not possible. 3 is the largest possible. It's the upper bound. Upper bound. Interesting phrasing, but it just means that's the largest possible factor there can be. The upper bound. So that means we don't even have to test this one. This one checked out. That is a factor. And so now we have x squared plus 3x plus 2. Right? And Descartes' rule of signs tells us change once right here. This changes twice. So there's only one positive root, which means we don't have to test those as well. 3 is the only positive root there can be because it only changed signs in one time. And this told us it was the largest possible. Now let's look at the other part of it. If b is less than 0 and the numbers in the last row alternate positive and negative, 0 can count as either one, then that is the lower bound. Okay. So what do they test there? They test -3. So let's do -3. 1, 0, -7, -6. Bring the 1 down. -3 times 1 is -3. 0 plus -3 is -3. -3 times -3 is a positive 9. Add those together. That's a 2. -3. Is that right? Am I doing all right? That's -6. That's -12. Okay. Did they get -12 in that? Yes, they did. They alternate positive, negative, positive, negative. This is the lower bound, which means it can't be smaller than -3. We can cross -6 off because this was positive, negative, positive, negative. Now, this is not one of the factors. That didn't work either, but it can't be any smaller than that because we hit a lower bound limit. We hit alternating positive, negative, positive, negative. So that helped us eliminate this as well. That's how that positive and negative upper bound, lower bound rule goes. It says, what do we know about an upper and lower bound? Suppose we have a list of rational roots like 1, 2, 3, and 6, and we try x equals 2, and we find out it is an upper bound. We automatically know there can't be any root larger than x equals 2, so that means we won't even test 3 or 6. We know they cannot produce a remainder of 0. So that's where the upper and lower bounds really help us, is eliminating how much we have to test. So we started out with 8 numbers that we would have to test to find the roots of this equation. We have tested 2 of them and eliminated the other 4 up here. So this is the only thing left to test. Is that the other 2 roots, or are they imaginary? So that means since this has 3 roots, 1 of them is positive, 2 of them are negative or imaginary, we only have to test 1 of these. If we test 1 of them and it is not a root, there's no need to check the other one because it has to be both imaginary. Because there's only 3, we have 1 positive. That means there's 2 negative or 2 imaginary because they always come in pairs. So we have cut 8 numbers down to 3, really. We check this one, and either one of those. Either one of those. Which, by the way, in this case, both of those will work. So those are the 3 roots. We can check that by graphing it. X to the third minus 7x plus 6. Let's graph it just to satisfy that curiosity. So let's graph the whole thing. X to the third minus 7x minus 6. What are the roots? 3, 1, -2. See, those were both good. -1 and -2 both work. 3, -1, -2, because we see it on the graph. Those are the 3 zeros. Those are the 3 solutions. Those are the 3 roots. But algebraically, we eliminated a whole lot of work of just not knowing anything at the beginning. Boy, that could be any number. Well, the rational root theorem, or the rational zero theorem, narrowed it down to 8. Descartes said there's only 1 positive, so if we check this one, we know the upper bound says it can't be larger. And since that had a remainder of 0, the remainder theorem said that's a root. So that allowed us to cancel all the rest of them. We checked -3. It said there's nothing lower than -3. Cancel that. We check -2. It may have be a lower bound as well. Nothing smaller than -2 because -2 is actually a solution. So a lot in this lesson. This is find the upper and lower bounds. And you can check your answers right here, going through there. And it can be there could be more than one lower bound or up or lower. Like if I would have checked -2, let's do that real quick because I want to see what that is. So this is 1, 0, -6, or -7, -6. The 1 comes down, multiply, add, multiply, add. So right, +4, yeah. Multiply 0. Okay, this one has positive, negative, negative, and 0. This could be counted as a positive or negative. This is not a lower bound, but it is a 0. Since the remainder is 0, that tells us that that is a 0. But this was the lower, that means nothing can be lower than that. But this actually gave us the answer. And since that's a 0, that means that has to be 0 because there's only 3 and it can't be imaginary. It cannot be imaginary. All right. And then there's more. Then we get into the lesson part of it. We're out of the summary. This just gives more detailed examples. More, it repeats everything, but it has more details, has more graphs. If you want to go through that, if there's anything else that you need clarification on. Let's look at, can't believe we made it through there. Let's look at what the assignment looks like. Divide using synthetic division. And then say what it equals. Looks like it's going to have a remainder. There's going to be a remainder. They want you to use synthetic division. Now here's the important part of this one. I'm gonna write that down real quick because if you're working, if you have this problem, you may not have this problem. You may have a different one. You may have a different one, but I would be expecting it would have the same issue, even if it's not the exact same one. You have 3x to the 5th plus 4x to the 4th. If I'm going to set this up with synthetic division, if this is x plus 2, I'm dividing by -2. Negative, whatever makes that 0, -2. Then I just take the coefficients, but I have to acknowledge the missing terms. What's my x to the 5th? It's a 3. What's my x to the 4th? It's a 4. What's my x to the 3rd? It's a 0. What's my x squared? It's a 2. What's my x? It's a 0. And then what's the constant? This is the synthetic division for this because you have to acknowledge every term, and 2 of them have a 0 coefficient. They're there, but they have a 0 coefficient, so we don't run them down. So doing that, you can make the division and end up with one of these 4. Here's one, divide f of x by d of x. Here's what d of x is. You cannot do synthetic division on this one because it has an x squared. You can only use synthetic division when it's just an x plus something or an x minus something. You cannot do synthetic with x squared. So that's one with long division. Find the remainder when this is divided by -2. So you can do synthetic division straight there, or you can substitute -2 in. Remember, we proved it'll work either way to find the remainder. Use synthetic division to determine whether the number k is an upper bound or a lower bound. So this one says k equals 3, and it's an upper bound. Yes or no? Is that an upper bound if you divide 3 into there? So you can test that. And use the rational zero theorem to list all the possible zeros. That's where you have the p and the q. I'm sorry, the p and the q. You list all the factors of that, divide p by q, and then list all the terms. And please, if you're doing this, use this. If I'm doing, there is a symbol Where's it at? There it is, plus or minus. It has a plus or minus symbol. It's plus or minus 1, plus or minus 2, plus or minus 4. And I would list the P's or something like P equals plus or minus 1, plus or minus 2, plus or minus 4. Then I would list my Q's, Q equals, and then I would finally list my final factors. But you can make it look right by using the insert equation button right there, where it looks nice and clean and neat. Shockingly, we got through all of that. I hope it didn't rush it too much. I'll try and take pictures of this stuff that we wrote down and put it in Google Classroom so you have that. If you get lost on this, confused trying to do this, come to class Thursday. Come see me, and we'll go through that. I don't think anyone's an RTI. Everyone's doing a pretty good job of keeping up. There may be one person or so, but if you're behind, get caught up. Everyone in this class is doing really well overall, so it's you guys are getting it. But I know I threw a lot at you today. I apologize for that. There's a lot in that lesson, and especially finishing up the last lesson. But if you have problems with it, email me or come see me Thursday during class or whatever. We'll figure it out. So, guys, have a great week. You got 5 questions this week. Have fun with it. We'll see you next time.